In this video, we're going to take a look and see how we can find a Jacobian using MATLAB. And you might recall that to be able to find a Jacobian, you just take a determinant of partial derivatives if you have a definition of a parameterization. So let's say for some reason we have a parameterization x equals 2u and y equals 4v plus 2u. So we had like that change of variable from one base x and y to another base u and v. And so to be able to find the Jacobian in MATLAB, we're going to define symbolic variables. We're going to go ahead and define what x and y are going to be. We're going to make a row vector f and then a row vector p. F is going to be the variable definition. So x equals 2u, y equals 2v plus 4v plus 2u. And then finally, p is going to be the variables with which we are taking the derivatives with respect to. We have this function Jacobian, and I just assign it to a variable j. And then we're going to find the determinant of j. And that's going to help us to be able to find this Jacobian. So we're going to take a look at two fairly basic examples of being able to use MATLAB to find the Jacobian. So first one we have is just going to be in two variables, x equals u squared minus v squared, and then y equals u squared plus v squared. Symbolic variables, u and v, definition of x. So that's going to be u squared minus v squared. And definition of y, which is going to be u squared plus v squared. And then we're going to go ahead and define our vector f, which is going to be x comma y, and then our vector p, which is going to be u comma v. And then we're going to find the Jacobian. I'm going to assign it to variable j. And that's going to be f comma p. And then finally, we are going to find the determinant of j. All right, now I did leave this unsuppressed for the first time we do this, just so that way you can see what the output is for this. All right, so we'll go ahead and run it. All right, so what we get is we get the matrix of partials. All right, so for instance, if you're doing a problem and you're having difficulty getting the Jacobian for that, then you can just go ahead and type in this code and you can just leave it unsuppressed. And then this just tells us what that Jacobian is. All right, so pretty cool that we can be able to utilize MATLAB to find those determinants as well as the Jacobian. Now, let's say we have a three-dimensional sort of Jacobian. So I'm going to add another symbolic variable or other symbolic variables here. So we're going to have a, b, and r. And what we're doing is we're looking at this example. So we have x equals r sine a cos b, y equals r cos b, z equals r sine a. So maybe you're working with, some sort of other coordinate system. For instance, this might look similar to your spherical coordinates or cylindrical coordinates, just a little bit. It's not the same. It's not holistically either of those. So let's define x to be equal to r times sine of a times cos of b. And then we're going to have variable y, which is going to be r cos of b. And then finally, we're going to have a variable z, which is going to be r sine of a. And now we're going to have a function, or we're going to have a row matrix f, which is now going to be x comma y comma z. Right? So we're dealing with three variables. And then finally, we're going to have a other matrix p, which is going to be in the form of r comma a comma b. All right. And it doesn't necessarily matter the order in which we do these. I just did them in the order that they were presented. All right. And then finally, I'm just going to find the Jacobian of f comma p. And then finally, I'm going to find the determinant of capital J. And again, I'm going to leave these unsuppressed so we can kind of see what happens with this. All right, so I'm going to go ahead and run it. And if I could spell Jacobian correctly, that would probably be helpful to execute it. All right, so look what happens here. We end up getting the matrix for the Jacobian, all right, except in 3 dimensions. And then when we go through and we evaluate the determinant, this is what we get. All right, so this would be kind of like that factor that we would multiply by to do the change of variable. Right. So hopefully this helps to be able to see how to utilize MATLAB to be able to get the Jacobians, and then also some of the applications of your iterated integrals as well.